Let's start off with a little calorimetry problem. We've got a block of ice and a chunk of iron. They're at different temperatures. We're throwing them together into an insulated container so no heat can go into or out of the system. It's all in the ice and the iron. And of course what happens is that heat always goes from a hot place to a cold place. That ice will never get colder and giving its heat to the iron. It will always heat up and the iron will cool down. And it'll continue to happen like that until we've hit some equilibrium temperature, till everything is the same temperature. Heat always goes from a hot place to a cold place. So I've sort of sketched it out here. As the iron moves down in temperature, the ice is going to move up until it gets to 0 degrees C, and then it's going to start to melt. And so we kind of have to figure out here, we don't really know where it's going to end up. Is all the ice going to get up to 0 degrees? Is it all going to melt and start to warm up a little bit? Are we going to have water and iron mixed together at maybe 5 degrees C? Or are we going to have some ice, some water, and some iron at 0 degrees C? We don't really know where we're going to end up. So I'm going to just figure out how much energy I have in the iron right now. Let's pretend for a minute that the iron cools all the way to 0 degrees. So let's figure out how much heat it would give off to the ice if it cooled all the way to 0 degrees. And then we'll figure out how much heat it takes to warm the ice up to 0 degrees and melt it all, and we'll see which one is more. If we have more heat in the iron than it takes to melt the ice, then we're going to have water and iron at some higher temperature. We have to go back and do some other things. If we don't have enough energy to melt all the ice, then we have to figure out how much of the ice melts. So let's just start out by figuring out how much energy do we have if the iron goes all the way to 0 degrees. And so Q, I'm going to call that Q1. That is equal to the mass of the iron times the specific heat capacity of the iron times its change in temperature. And so what do we have? We have 5 kilograms. We have 470. You have to find that in the book somewhere. Joules per kilogram Kelvin. And 750 minus 0 is our delta T is 750. I'm going to go ahead and mark it Kelvin. It's the same in Kelvin as it is in degrees Celsius because it's a delta T. And what I end up with is 1.76 times 10 to the 6th joules. So it gives off a fair amount of energy. Now let's figure out how much energy it takes to bring the ice up to 0 degrees and then melt it. So ice warms to 0 degrees C. Let's see how much energy it takes. I'm going to call that Q2, and that's going to equal the mass of the ice times its heat capacity times its change in temperature. 5 kilograms, 2100 joules per kilogram Kelvin, and 10 Kelvin is the change in temperature. And I get 1.05 times 10 to the 5th joules. So that's a lot less than what we have. So a little tiny portion here, let's just rewrite this one as 17.6 times 10 to the 5th. And so we got 17.6 times 10 to the 5th joules out of our iron as it cooled, and we only have to put in 1.05 times 10 to the fifth to warm the ice up from negative 10 degrees to 0 degrees. So that means we still have over 16 times 10 to the fifth joules. So let's see what it takes to melt all the ice. So a phase change, we're going to call that Q3. And when we have a phase change, it's the mass times the heat of fusion. And what do we end up with? 5 kilograms of ice and 334 times 10 cubed joules per kilogram, is that right? And I end up with 1.67 times 10 to the sixth joules, which is 16.7 times 10 to the fifth. And I don't think I have enough. Let's see how much I have available to melt. I don't think I have enough to melt it all. Let's see. So heat available to melt the ice is going to be equal to Q1 minus Q2, right? Q1 was how much heat we got from this 17.6 times 10 to the fifth. But we used some of it. We used 1.05 times 10 to the fifth to bring the ice up to 0 degrees. So we used some of it up. And that leaves us with 16.55 times 10 to the fifth joules. So we only have 16.55 times 10 to the fifth joules left. And in order to melt all the ice, it would take 16.7 times 10 to the fifth. So we don't have enough energy to melt all the ice. So not all the ice melts. Now we need to figure out how much does melt. Well, we kind of have the answer here. This is telling us how much heat is available to melt ice, so why don't we solve for how much ice melts. So to melt ice, we know that Q is equal to M times the heat of fusion, and we know we have 16.55 times 10 to the fifth joules available to melt the ice. We don't know how much is going to melt, but we do know the latent heat of fusion. And so this tells us how much melts. 4.955 kilograms of ice melts. So in the end, after everything's reached equilibrium, we have a mixture. We have 5 kilograms of iron. We have 4.955 kilograms of water, and we have 0.045 kilograms of ice, and all of that mixture, that ice, iron, water mixture is at 0 degrees C. So the idea here is the only items in our system are the ice and the iron. We're ignoring the effects of the container. We're saying it can't absorb heat or give heat, and it's perfectly insulated. So all the heat to warm up and melt the ice had to come from the iron, and we just are trying to figure out at what temperature everything ends up. And if we have an ice-water-iron mixture at 0 degrees, or a water-iron mixture higher than that, at some temperature higher than that, and we could figure that out. So all the heat comes from the hot item, goes to the cold item, and everything eventually ends up at the same temperature.